morning, or actually afternoon now. I'm a software engineer at Red Hat, working on a team that is building out the RAD Analytics IO community project, and we are working on exploring Apache Spark deployments on OpenShift, and also more generally Apache Spark as an engine for intelligent applications in the cloud. So today's talk, I'm going to start by defining what feature reduction is, and then hope to persuade you why it matters. And I'm going to do a couple of brief detours for a crash review of random forest clustering and T-digest feature sketching. I'm going to then tie those ideas together to explain how they're used to do random forest feature reduction. Then I'm going to do a short example results on TOX21 assay data. So show of hands, how many people here feel comfortable with what a feature vector actually is? Oh, good. That's almost all of you. That's good news for my talk. So features are, of course, just basically measurable properties of an object, and we generally measure as many of these things as we can for our objects to do learning models, and we assemble them into feature vectors. The feature vectors are, of course, our inputs to the model training algorithms, and then once we have a model, they're the same inputs to the evaluation to do model inference. So feature reduction is when you start with some full feature set, you identify which features are actually useful or most useful for your learning problem and discard the rest. And so what's left is a feature set of reduced size. Why would we want to do this? Well, feature sets can actually be quite large. Feature sets, hundreds or thousands of dimensions, are not at all uncommon. For some domains, you can actually get feature sets running into the millions. So it's worth trying to make these things smaller. Features are not free. They're data, and so if you have smaller feature vectors, you're using less memory, less network, and less disk. They're faster to operate on, so you can save time. If you are in an embedded environment or Internet of Things kind of application, smaller feature vectors translate into lower energy usage. Another aspect of this is that a lot of features can be noisy, and in fact, they can be so noisy that they're more harmful than they are helpful. And they basically represent a kind of a data pollution that's going into your algorithms. Many algorithms are totally capable of adapting to noise in the data, but the best you can hope for is that they're going to ignore it, and they may not ignore it perfectly. So conversely, if you can give it a reduced set, which a lot of these noisy features are removed ahead of time, your model is actually going to have an easier time training, and you're going to get less risk of model distortion from this kind of feature pollution. So all things being equal, a larger feature vector usually translates into a larger model. And so if you've got a whole bunch of otherwise useless features going into your model, it's basically going to result in a model bloat. So you get a model that's larger than it needs to be and probably slower than it needs to be. Again, conversely, if you can give a reduced feature vector to your model, you're going to get a leaner, potentially faster model. So I noticed yesterday the representation learning and transfer learning got a bunch of buzz, which is very good, and so I thought I'd throw in a special bonus slide about that. Just to point out that you can do feature reduction on the vectors coming out of a transfer learning scenario. So you're not just stuck with the exact features that are coming out of somebody's existing model that you're trying to do your transfer learning on. First detour, crash review of random forest clustering. Random forests were introduced by Leo Brayman in 2001, and they are a kind of decision tree ensemble model where each tree is trained on some random subset of the data, and each split in the tree is considering some random subset of the features at any given time. And the basic approach to random forest clustering works like this. You take your raw feature vectors and you evaluate them against some random forest model that you've trained. And while you're doing this, you keep track for each tree of which leaf node that vector actually landed at, and you collect those into a vector like the one you see on the right. And the trick is you cluster those vectors of leaf IDs. So this is not a talk about clustering, so why do I care about that? Well, two of the key reasons that random forest clustering works well is that the random forest training itself automatically figures out which features weren't useful for it, and it throws them out. And furthermore, the number of features that the random forest actually uses is often much smaller than the full feature set. So you can begin to see how these properties might represent the foundation of a feature reduction technology. So how does this actually play out when you apply the method? You start with your actual raw feature data, and as in this toy two-dimensional example, it occupies some subset of your feature space. You then generate some synthetic data, and this synthetic data has this property where the marginal distribution for each feature column is exactly the same as in your actual real data. But you've lost the joint information because they're sampled independently. So you can see these pink dots here are the synthetic data, and if you projected them along each axis, you'd see they have the same marginal, but you've lost the joint. And so now that you have some real data and some spread out synthetic data, you're going to train a random forest to learn which are the real data points and which are the fake ones. And so what you've done basically is persuaded your model to try and learn where your real data lives in the feature space. So now that you have a model, you can actually examine each tree to pull out clauses that represent the paths down the tree that you can take. And so this one in blue here is one I'm going to use for the example. And each of these clauses in this, again, toy two-dimensional example can be drawn as kind of like a quarter plane, like the one on the right. You can actually overlay these on the original data to see and verify that it did actually learn where your real data lived in the feature space. Now you want to imagine this happening in hundreds of dimensions, but of course I can't draw that and you can't see it. So going back to the model, you can do another thing with the inspection. You can just examine to see what features in the tree were actually used and collect them up. And you can take that as a reduced feature set. So again, in this example, I didn't reduce the feature size at all, but I only started with 2 dimensions to begin with, so there wasn't a lot of reduction to happen there. Second detour, a brief description of T-digest sketching. A T-digest is a sketching data structure that represents the cumulative distribution function of some data that you give it. In our case, these numbers coming in are going to be feature values. Why would I want one of these cumulative distributions? It turns out that if you have the CDF of a distribution, you can do a trick called inverse transform sampling to actually sample from the corresponding distribution. And that sounds fancy, but all you really do is pick a random number from the uniform distribution on 0 to 1, and then you figure out the value of x in the feature space where such that the CDFX is equal to that random variable. You can do this in logarithmic time. It's very fast. So with this data structure, I actually have a way to synthetically generate feature values from the original distribution of my data. A nice property of T-digest is they aggregate very well, and that's a fancy way of saying that they work very well with Spark's commodity scale-out parallelism compute model. So you have data in Spark, and it's distributed across partitions. So for each partition, you can basically compute the t-digest, and then at the very end, you can combine them into a single final result. What does this actually look like? It's literally as simple as it sounds. You can use the Spark's aggregate methods. And the first line is basically per partition, you're assembling a sketch, and then when it starts to combine the partitions at the end, you do, sort of monoidal combinations. So we have feature vectors, and so we're actually assembling vectors of these t-digests. And once you have that, it's equally easy to generate your synthetic data. You just broadcast it if you want to for efficiency, and then pick your size n for the number of data points you want to generate, and for each row in the output RDD, you just sample from the vector once. It's fast, it's easy to code. And so with all these pieces, we now have, again, a super simple method for generating the training data for these random forests. You start by sketching your actual training data, generate some fake data. You label the real data 1 and the fake data 0, and you paste those together and send that to your random forest training algorithm. So let's put it all together to see how this looks like when you run it all together. You have your real data existing in some part of your feature space. You perform a sketch for each of your features, use that to generate your synthetic data, train the random forest to distinguish your data from the synthetic, and then you examine the model that you got and pick the features that the trees actually use. And hopefully it's a lot smaller than the full set. So I'm going to give you some example results, what this can look like. I used the TOX21 data, which was from a competition sponsored by the National Institute of Health in 2014. They provided 12 toxicity assays run on about 12,000 compounds and about 650 held out as a testing evaluation set. The particular format of this data that I used was compiled by Johannes Kepler University on their Deep Tox project. So I just wanted to give credit to them for the data that I actually sucked into my system. So what is the shape of this data? There are 801 chemical features, chemical structure features that are dense, basically, that are present for everybody. And there are also 270,000 sparse features. I did not use those for this example demo. I just stuck with the 800 dense ones. Each assay was not conducted on all of the data, and in fact, each assay was conducted on a slightly different subset of the data. You can see kind of like what that looks like in this clip of the table that I showed up here. So my experiment was I trained some Spark ML models on all 12 of these assays. So there's basically 12 learning problems here. I then performed some random forest feature reduction, and I trained corresponding models on this reduced set. And so then I compare the models trained on the full set with the reduced set, and we want to see, hopefully, similar performance. So when I did the feature reduction, in this case, 85 out of the 800 features were used. So I reduced the number of features by nearly 90%. And this was the top 10. I kind of histogrammed them by how many trees actually used the feature. So the top one here, RNCS, was used on 21 of the 100 trees in the ensemble that I trained. If you're a chemist, you might know what these features are. I really don't. So the first model I trained was logistic regression, and these orange bars are the model accuracy based on the full features. And then the dark blue and the light blue are basically trained on the 85-dimensional reduced set. So the first thing you can see here is that effectively the performance was the same. That's really the thing I'd like you to take away from this is you've suffered no loss in performance. In fact, these dark blue bars are actually cases where the model on the reduced set actually did slightly better. So on more than half of them, not only did you not lose any performance, you technically gained a little bit. So a second model I trained was just a boosted decision tree ensemble. And here you can see the story is essentially the same. You've got, most of the cases you actually achieved a slight increase in model accuracy, and in a few cases it was slightly lower, but generally speaking, it's totally comparable. The last model I trained was a support vector machine. And again, the basic story is unchanged. I would call your attention to the assay there in the middle, where for reasons unknown to me, the reduced feature set failed dramatically. It's like scoring 10%. So I thought I'd leave that in there as a teachable moment. There's no such thing as a tool you can apply blindly. So there's a couple properties of all this I wanted to call out. The first is the feature reduction happened without any knowledge of the domains. There was no knowledge about the 12 assay truth columns at all. And I performed the reduction before I trained a single model. So you can see that you can actually perform a reduction that not only works across 12 different domains that it hadn't seen, but it works across a variety of learning models as well. Earlier I claimed that these models were cheaper to operate on, so the training times you can see were basically substantially less, not 90% less, but there's a lot of stuff going on in Spark. And you can see for the SVM, the difference was actually very small. Evaluation times were better. For logistic regression, you actually get effectively a 90% speed increase. For SVMs and the ensembles, it was not 90%, but on the order of half. So that concludes the talk. At the bottom here, there's a URL that contains the notebook I used to actually assemble and collect all the data. So I encourage you to go look at that if you want to try and replicate the results or use it on your tools. Thanks a lot.
Questions on the aisles? Yeah. What determined 85 as the number of reduced features rather than 75 or 95?
Well, again, it was just based on what the ensemble used when it was learning to distinguish the real data from the synthetic data. I didn't put this in the slides. What I actually did was I picked any feature that was used at least twice. So there was about 150 or so that were used, but a lot of them were only used once, and I figured, well, maybe that's just a fluke. And if you run it, you can run this different times, and the number will fluctuate a little bit because it is random.
So you talked about synthetic data, but how can we generate synthetic data that looks different from the real data? Is it a random generator? What went into it?
Yeah, so again, the idea is that you want to create your feature columns so that the marginal distribution is the same. So that if you looked at just a single column, it would have exactly the same distribution as your original real data. And in fact, when Leo Brayman originally did this, he had smaller data sets. He just literally randomly permuted each column. Of course, with modern data sets, you can't do that. So the T-digest was a method I used to scale that basic principle out to handle modern size data.
Hey, thanks for the talk. We did a similar thing using in a scikit-learn on a smaller data set, and we were able to reduce from 2,000 to around 30 features. We were doing that for ad marketing. I have a general question. So because feature selection is a pretty important step in modeling of the data, So, and it's hard to find what features affect your use cases just in the same company but different use cases. So as today I observed that you applied it on the Spark big data and you got a good result. So in general, if I say I want to find out the features which affect my use case, which is a newer use case, can I use it like 7 out of 10 times with a random forest and see what it comes out and then discuss or further improve that? What is in a general case if you want to apply for a new use cases that you started digging into it? Thank you.
Yes, if I understand your question, you can definitely run multiple runs of this and see what happens. I think to your point about also applying it to specific problem areas, I was deliberately trying to show that you actually don't have to have any knowledge of your domain, but you can do the same basic trick if you, say, train a random forest model on your problem. So you can actually train a recognizer to do a prediction instead of unsupervised. And in that way, you can still examine the model and see what features were used, and then kind of like retroactively go back and say, well, look, my trees are telling me that I only need like 10 of my 30, features. From now on, I'm just going to use those. And there's advantages to that because, of course, now you literally know that you were training trees exactly on the problem you're trying to predict. So that's a very useful technique too. I was trying to show that you literally don't even need to do that.
On top of that, how do you think using this would help in an anomaly? Let's say my feature selection is good with, in most of the general cases, but if there is an anomaly in the data that which I need to account for because of its value, not always, but sometimes it's a value to me, would this model help to add that to the data?
I don't have like a short answer to that. Can I take that offline with you?
Thanks for the talk. A quick question. So for demonstrate, use random forest, we also can, for the features, we also can have the variable importance. So there's one way, we probably just train our problem and choose the features and ranking based on their variable importance. So then we can select the most important feature based on that score and probably also retrain the problem as well. So what's the differences between if I just use a variable importance from random forest versus the method you used here? Do you compare this before?
Oh, yeah. So if I understand your question, you're just saying, what if I just train a random forest and it uses the features it uses and...
Yeah, like I probably just train my problem and then I probably have 30 features, but I can rank them based on their variable importance. I can choose probably the 10 most important features. Then I probably can retrain my model because I don't have so much noise, for example. Then I probably can get some results. Then versus the method you provide, what's the differences between the insights of the two?
Right. Yeah, I think that you're saying, you can basically, it's kind of like a hyperparameter you're playing with, how many of these things you're actually going to pick. And, in real life, there's likely to be, a trade-off space there. Like I said, in my examples, I just kind of semi-arbitrarily said, well, if it was used at least twice, I'm going to keep it. And that seemed to work well in this domain. It may be that in some domains, I could have just picked the top 10 and reduced it even more and still kept my performance. When you apply this in the real world, you're likely to want to experiment with a few different points like that to get a feel for how it's affecting your accuracy.
Second, really quick question, which is a clarification question. So when you, for the method you're using, so first you have the real data, and second, you generate the synthetic data. So when you do a feature reduction, you just give labels for all the real data 1, and give synthetic data label 0. and then you just find the features. But the real problem could be regression problem, could be the classification problem. So, but in order to find the features, you just real data label 1, synthetic label 0.
That's right, it just becomes a two-class problem. And as I was trying to explain earlier too, if you have like a regression problem, you can train a regression ensemble and see what features it used. So, I mean, that's definitely an option that's worth exploring, especially because that actually gives you some assurance that it was tuned to exactly learning your problem. But here, I guess, is trying to point out that just learning where your data lives inside your feature space actually gives you a surprising amount of information about like which features are useful or not.
Thank you so much.
First of all, thanks for the talk. That was really, really fascinating. I had a question around one of the things that I sort of struggle with in applied work is maybe not sort of data sets with lots of unnecessary dimensions, but maybe data sets with sort of high cardinality categorical features. And I'm curious to know if you have any thoughts on like, could this be used for those kind of problems?
Yeah, I'm quite sure it could. Like the features I was using didn't have that. They're basically numeric. But as you know, of course, you can basically go to one-hot encodings, and it's still basically going to learn. It'll learn which subsets of those just as easily as it learns subsets of anything else. So it might, interesting, in that case, it might tell you it's like all I really care about is whether or not it's a member of this category. And whether or not it's a member of those other ones, it doesn't matter.
I have a quick question. So basically, for feature reduction, you generally like in R or Python, you can use like Elastinite or like Lasso to do feature reduction. So have you compared with that?
Yeah, that's a great question. In preparing this talk, I didn't do really any experiments comparing with like alternative methods. I was just kind of like trying to demonstrate that this is a method that, that work very well.
Yeah.
No, that's a great question. I think that would actually make another talk.
Yeah, totally. Okay, thank you.
All right, let's thank Erik once again.